Equilibrium problems. It's possible I'm losing my equilibrium. This is like the 5th time I try to record this. It'll work this time. Okay, so here's an AP practice problem that requires the use of rice tables. So let's do this. Here is the problem. Classic AP. It's got parts A through E. It's got Roman numerals. It's got all the good stuff. Okay, so let's see what it's about. We have hydrogen sulfide gas. Is that important? Yes, it's important for equilibrium. We need things to be either gases or in solution. So check everybody else. Everybody else is a gas. They're all going to participate in this equilibrium. Okay, we have a 3.4 gram sample of H2S. Okay, I've got some of this. And then evacuated. Evacuated means empty, completely empty of all things. Rigid, meaning the volume will not change. 1.25 liter container. Great. It is sealed and it's heated to blah Kelvin. Good to know that it's in Kelvin. And blah moles of S2 is present at equilibrium. I would totally underline that. I know I have information about what happens in the beginning, and I have information about what happens at equilibrium. That will totally be useful. Okay, so it's an equilibrium problem. I'm dealing with gases. I have initial information and I have equilibrium information. I think that's the important part. So let us carry on. In general, we are going to use, these are the 4 main ways that I organize work for these problems. It doesn't have to be the way you organize work, but it is useful. It's useful to know if you get stuck somewhere, what's the next thing I can try? Let me try a rice table. If I don't know what's the next thing I can try, let me find Q. I don't have Q yet. But usually the problem in the part A, B, C will tell you where you have to start. But just as a reminder, a rice table will help you determine equilibrium conditions. Q will help you determine the direction of the reaction. K and the E part of the rice table are usually related to each other by this X, this change thing. And that's a useful thing to know. And make sure to read the question and make sure that you answer the question. In these problems, there's a lot of solving for X. And unlike a math problem, we're not asking you for X. We're asking you for something else that X is involved in. So don't stop at the, oh, I solved this. Read the question again and make sure that you're answering the question. So this is how I'm organizing things. In general, I use the rice table to organize information. So as I get information, I will put it into the rice table, even if I'm working on something else. I should set up the equilibrium expression. That's an important piece of information that I will use. Q is often helpful, and it's the combination of the K and the rice that usually gives you the equation that will help you solve. Not always, but usually. Okay, so again, this is the fabulous color scheme of my 4 steps. If I had the space, if I had 2 whiteboards full of space, I would physically organize it this way. So you've got paper in front of you. I would turn it that way, the landscape way, just to try it out. Maybe you don't like it. Maybe you like things to be linear, but give it a try. So before I begin, go get paper, go get pencil, go get calculator. The periodic table nearby is always useful too, and you will do the problem with me. Okay, so part A. We already looked at what information we were given. Part A asks us for the expression for the equilibrium constant Kc. So hopefully the terms expression and equilibrium remind you or make you think that, oh, I need that K equals concentration of the products raised to whatever power over concentration of reactants raised to whatever power. You don't have to memorize this. It's on the equation sheet. This is also an open book test, so you need to know how to apply it. So let's practice how to apply it. So it's Kc. This is the reaction. These are the coefficients. Pause the video and write yours out, and then we'll compare. Okay, so my value for the K expression is the concentration of hydrogen gas squared, because of the coefficient of 2, times the concentration of S2 over the concentration of hydrogen sulfide squared, because of this coefficient. That's it. 1 point on the AP. Woo-hoo. Did I answer the question? Yes. I'm done. For part B, calculate the equilibrium concentration in moles liter to the negative first. Blah, ugly unit. Don't worry, the College Board loves to write units this way. I'm giving the benefit of the doubt, and I'm assuming that it's because formatting is difficult, but maybe they're just evil. That just means mole per liter. So something to the -1 is just divided by that amount. So mole per liter, that's a molar. You could have just written the capital M. It's all good. So we want the equilibrium concentration in moles per liter of the following gases in that same container at 483 Kelvin. It's nice to know that we're at the same temperature that we were given information in, and which gases are there? H2 and H2S. So those are the two that we need, H2 and H2S. I've got some information about S that might be useful. Okay, so next step is organize all of the information we have into a rice table. So R is for reaction. Write out your reaction with plenty of space. I like putting a line at the yield sign to divide reactants from products. I, initial conditions. Tell me what you know about what's going on at the beginning. C is for the change. E is for equilibrium. Maybe you don't do all of it. Maybe just write in the initial conditions for now. And pause me before we go to the next one. Okay, so the initial conditions. Nobody said anything about hydrogen or sulfide gases. It did say it was an evacuated container. Therefore, there was none of that stuff. It didn't even have to say an evacuated container. It could have just said this much was added to a container. If the species was not mentioned, you assume that it was not there in the initial conditions. So initial conditions are described literally. If it was there, somebody should tell me. Be careful for things like something happening in an open container or something happening in the air. That means that there is oxygen or there is N2 or there is some carbon dioxide or whatever. But that doesn't usually happen. So I have some initial conditions. I also know exactly how much H2S I have. Can I just write 3.4 grams? No. These units are not grams. These units are not moles. They are moles per liter. This is in terms of concentration. It's Kc. The only other option is if you're doing a Kp problem, those should be in units of pressure. So whatever unit of pressure you're using, atmospheres, kilopascals, as long as you're consistent and you use the same unit for every step, you're fine. Okay, but no, we're in moles per liter. So I have grams and I have liters. If only I knew how to get from grams to liters. Oh wait, I totally know how to do that. So take a second, find me how many moles that is while I inch this little thing over here. There we go. So to find that, we need the molar mass. So you need to find the molar mass of hydrogen and sulfur, of two hydrogens in fact. So this is the molar mass of H2S, 34.08 grams per mole. Unless I've made a mistake, in which case please tell me. So how do I get from 3.4 grams to moles? I divide by molar mass. If you notice, that way the grams cancel and I'm left with moles, which is what I want. So look at that. So 3.4 divided by 34, I should get about 1/10, because 34 is 10 times bigger than 3.4. And that's really close to a tenth. 0.0998. I took 3 sig figs. Was that a wise thing to do? Yes. All of the information given in the problem was in 3 sig figs. So, moles. Almost there, but not quite. I do not write mole in the rice table. I write molar, moles per liter. I have the moles. I know the liters, so let's just divide. And that's 0.0798 molar H2S. That is a number that you can write in a rice table. I don't usually put units in a rice table because all of these are units of molar or atmospheres. So I tend not to do that. If you might be in danger of messing up your units, write the units in. I'm just trying to think, are there any other units? I do use millimole per liter sometimes. Okay, so that is my completed initial conditions. Okay, let's use the rice table. How do I do that? I need to figure out what's going to happen next. So in this case, I'm starting with 0 molar of 2 of the products. If any of those, any species, either a product or a reactant, if any of them is 0, I can only increase. I cannot have less than 0 of something. No negative numbers. This is counting. We can't have less than 0 molecules of something. It's just not a thing. So we need positive numbers. So if you ever see a 0, that means that quantity is going to be increased. Therefore, everything on that side is going to be increased, and the opposite side is going to be decreased. But sometimes there might not be a 0. Those might just be numbers. How do you figure out what direction you're going to go in? You calculate Q and compare it to K. So what would that look like? If I were looking for Q, which is a little yellow thing, there it is, I would, I've just made myself disappear. That's not cool. Well, I have in fact disappeared. Such is life. Okay, so Q equals 0 times 0 divided by whatever is 0. So what does that tell me? K, I don't know what K is, but it's got to be a positive number. Therefore, it's got to be larger than Q. Therefore, Q is going to tend towards K, meaning the whole reaction is going to move to the right. It's going to produce products. Okay, so moving to the right means there are positive signs on the product side, negative signs on the reactant side. How do I know how much has moved? I don't know how much has moved, but I do know that the amount that the H2S moves is going to be twice as much as the amount that the S2 moves. So I use the coefficients to figure out how big the motion is. So the coefficient is 2. For every 2x that I lose, I create 2x of H2 and 1x of S2. Using the coefficients. This is the only place in the rice table where I use the coefficients. So please notice the 0.0789. That was the moles per liter of H2S, not of 2 moles of H2S. this amount corresponds to this species. There is 0 H2, there is 0 S2. So in the initial conditions and in the equilibrium conditions, I'm just describing how much of that specific compound or element or ion or whatever it is. That's why I'm saying species. The change takes into account the chemical relationship between the two. That's where the coefficients come in. So now I'm going to put these together. Initial conditions plus the change make the equilibrium conditions. So you just write out 0.0789 plus negative 2x, or 0.0789 minus 2x. 0 plus 2x, 2x, x. Those are the equilibrium conditions of the three compounds. Now, there's one more bit of information that I have not included in the rice table yet, and that is this lovely sentence. 3.72 times 10 to the minus 2 moles of S2 is present at equilibrium. That's a fragment of a sentence. Whatever. Okay, so that clearly relates to X. So X is the concentration of S2 at equilibrium. Is this a concentration? No, but it's most of the way to a concentration. So it tells me the moles. To get to the concentration, I divide by 1.25 liters. This is the concentration at equilibrium, 0.0298 molar. Equilibrium condition of S2 gas. That means that I know what X equals. X equals the equilibrium condition of S2 gas. Therefore, X equals 0.0298 molar. I know what X is. Therefore, I know how to calculate 2X, the concentration of H2, and I know how to find the concentration of H2S. So the next couple of steps are just plugging in. Just as an aside, I like writing the values near the rice table. So I wrote, you can't see it, 0.0298 right there. Okay. As I get more information, I'm going to write it there as well. So how do I find 2x? I multiply x by 2, 0.0596, and that will be the concentration that I write for H2S. Then I'm going to use that concentration for then I'm going to use that concentration to find the equilibrium constant of H2S. Okay, let's do this. 0.0789 minus 2x is 0.0193 molar. So now I have all three equilibrium conditions. Did they ask me for all three equilibrium conditions? No, they only asked me for two of them. Let me make sure that I'm reporting the correct ones. Yep, H2 and H2S, equilibrium concentrations. You don't have to write this E. I find it useful to distinguish between the initial conditions, which I usually write a 0 for. You could write an I, that would be reasonable as well, and the conditions at equilibrium. So I'm done with part B. Part C. Calculate the value of the equilibrium constant, Kc, for the decomposition reaction. Okay, so I was asked for the expression of the equilibrium constant. Now I want the value. So I'm going to use the expression from part A, and I'm going to use the values at equilibrium that I got from part B. So take a second, plug them in, use the calculator that you are getting used to, and make sure you square the correct things in the numerator and denominator. Okay, so this is the expression, and I'm going to plug in those values in the correct places. So if my calculator has not led me astray. The K for this expression is 0.284. Again, let me know if I'm making mistakes. Part C, check. Okay, part D. Calculate the partial pressure of S2 in the container at equilibrium at 483 K. So, depends where your brain is right now. If your brain is, like, I just found KC, I know KC and KP are related, I can find KP, and I can work backwards to figure out what the partial pressure of S2 is. Yes, that would probably work. Yes, it will definitely work. But why go to all that trouble when you can just do the ideal gas law? So there are often parts in these long problems that are just a matter of applying stuff from earlier in the year. So even if it's an equilibrium problem or a kinetics problem, often there are bits that you can do just with stoichiometry or just with gas laws. So read through a problem. Just because you don't know how to do part A, do not give up on the problem. All right, so partial pressure, ideal gas law. Well, for the ideal gas law, I need volume, I need moles, and I need temperature. Oh, look, volume, moles, temperature. So solve this, and then unpause me. Moles of S2, partial pressure of S2, check. 0.0821. If you want to use 0.08206, you'll get a slightly different answer, I think, but it's all good. Again, I am rounding to 3 sig figs because all of my numbers are in 3 sig figs. Times the temperature. It was already in Kelvin, so I didn't have to add the 273, and the volume in liters. So the partial pressure of S2 at equilibrium is 1.18 atmospheres. Check. Part E. For the reaction, H2 plus 1/2 S2 makes H2S at the same temperature. Calculate the value of the equilibrium constant Kc. So I'm given a new reaction and no new information. What's up with that? Well, hopefully you should notice that these two are related reactions. Equation E is the main one reversed and divided by 2. So maybe you wouldn't see that immediately. The reversed part, I think, is easier to see. And then you're like, oh wait, there's still, these guys are the same and that's half as much. These guys are the same and that's half as much. So we can use the fact that we know the K for this one, and we know what has to be changed to that K to get the new one. If that didn't make sense, let's just start comparing them. So I'm going to write out both expressions. There's the main one that we've been dealing with so far, and the purple one. So they involve the same 3 chemicals, and they've got the H2 and the S are on the same side, and the H2S is on the other side, and these two have larger exponents than the other guy. So you're looking for relationships. So I would start doing things to the main one. I want to move this around until I end up with the format for the purple one. I want to know, well, what do I have to do to my K, the one that I know, the 0.28, whatever it was, 4, I think, in order to get the purple K. So I'm going to start out by taking the square root of everybody. I could reverse it first, but it doesn't matter what order I do things in. So if I took the square root of everybody, square root of something squared is 1. Square root of something to the first power is square root. Square root of something squared is 1. So if I take the square root of k, oops, I'm going back and forth between multiple things. There. If I take the square root of k, I end up with an expression that's much closer to the purple one. Now all of the exponents are correct. The only problem is the reciprocal, and I'll handle that in a sec. But I wanted to show you that if I multiplied that entire reaction by 1/2, if I multiplied all of the coefficients by 1/2, I would have this expression. There'd be a 1 to the first power on H2S, first power on H2 to the 1/2 on S2. So if I multiply an equation by a number n, the k of the new one is the k of the old one to the nth power. That's a rule, it's just the math. Okay, now I'm trying to get this expression to equal that one. In order to do that, it looks like the only thing I have to do is flip it. I need to make my reactants equal my products. Make my numerator and my denominator reverse. So that is taking the reciprocal, or taking it to the negative first power. So whichever way makes you happier to think about things. I prefer to write 1 over k to the 1/2 than to write k to the negative 1/2. It is absolutely the same thing. But I want to show that if I take the reciprocal of this expression, I end up with exactly purple k. So to solve for purple k, the new reaction, all I have to do is take the reciprocal of the square root of the old k. I can do that. The reciprocal of the square root of the old k is 1.88. So the k of the new expression is 1.88. Moral of the story. If you know k of one equation, if you know the k for the original reaction was 0.284, you could find the k for the reverse. All you have to do is find the reciprocal. You can find the k for a reaction that is multiplied by any number. And how do I find the new k? I raise the old k to the power of the new factor. So that might have to sit with you for a while. You might have to practice a little bit, but that was the answer to part D. It was what is the Kc of this new purple reaction. So we are done. Let me find you the beginning. This is the problem. So we know how to write an expression for an equilibrium constant. We used the Rice table to find equilibrium concentrations by putting all of the information into the Rice table. All the information about the initial conditions, the C that we figured out on our own, and all the information for the equilibrium conditions, including this outside bit of information. If that's not given, then you plug in your expressions with your x's into k. But we didn't do that in this order. That's not what this problem asked for. Okay, part C is to find Kc, find the equilibrium constant. So we plugged in these values into that expression. Partial pressure, that was just an ideal gas law problem that was photobombing us. And for the next part, we found that I can ask you for the K of a related reaction. If you know that if it's flipped, reactants become products, you take the reciprocal. If the coefficients have been multiplied by something, you raise your k to the power of that thing. And that's it. So please practice more equilibrium problems. In our Schoology, there's a worksheet of a bunch of old AP problems. I will also add more to your College Board site assignments. So practice, 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 practice. I would say at least one a day from now to the day of the test. Okay, take care.